In this next unit, which is Unit 11, we will be looking at surface area and volume for the most part. Now, when we talk about surface area and volume, we first have to kind of backtrack and look at space figures and nets. Now, we're going to do the basics before we can get into like the formulas and finding the volume of a shape, surface area of a shape. This whole unit we are dealing with and talking about three-dimensional objects. Okay, if you talk about surface area or volume, you're talking about 3D figures, which we have not done yet. Okay, so this whole unit is about three-dimensional figures. Now, there's some vocab, which is what's kind of bulleted here at the top. So let's kind of fill this in together, and then we'll start looking at some diagrams. So we're going to be looking at polyhedrons. So that's our first term here. A polyhedron is a three-dimensional figure whose surfaces, or like every side of the shape, is a polygon. Okay, and remember polygons. So we've learned a lot about these, and basically they're just shapes, which you start doing those in elementary school. But remember, the definition formally of a polygon is a figure with at least three sides. So we're looking at 3D shapes, and every side of the shape is a polygon. Okay, that's a polyhedron. Now there's different parts to a polyhedron, and the first part is a face. And a face is a surface of the polyhedron, or basically just like one of the sides, the front of the box, the back of the box, whatever. It's one of the surfaces, which again, all of the surfaces are polygons. Okay, the next term is an edge. An edge is a segment that's formed by two different faces, or two different sides. The next term is a vertex, and a vertex is a point where three or more edges come together or intersect. And below, once we've kind of filled all this in, you guys, I'm going to point out to you on this blue three-dimensional figure here what's a face, what's an edge, and what's a vertex. Okay, so getting the definitions in first. The last little term here is what's called a net. And hopefully this is kind of familiar to you from like middle school geometry. But a net is just a two-dimensional. It's not 3D anymore. It's a two-dimensional pattern that you can fold up to form a 3D figure. So really, we're just going to be breaking down all of these vocab terms in all of the examples that follow here. So example 1, we've got this polyhedron, this three-dimensional figure here, and this polyhedron is called a cube. And it's called a cube because all 6 of its faces are squares. So when each side of your little box here is a square, you're looking at a cube. Now they want us to identify each piece. So like what every arrow is pointing to, and that's kind of where these definitions, you're going to get a visual for them. So like this bottom piece here, this bottom arrow, they're just pointing to like the right side of the box. And every side or every surface of the box is called a face. Okay, so that bottom one, that's a face, just one of the sides. Where two sides come together, which is what this middle arrow is pointing to, where the two sides come together, that is an edge. And then the top piece, top arrow, where your edges come together, or like one of the corners on this cube, that's called a vertex. Okay, so you need to know the difference between all 3 of these and being able to point them out in a picture and identify them as well. So the corners are the vertices, Where your sides come together, that's an edge, and each side is called a face. Okay, the next example, and I say this every year, these kinds of problems are come a lot more naturally to some people than they do others. Okay, so if you don't grasp this right off the bat, don't panic. It may just take some time. Not all of us can do these types of 3D thinking problems in our head. So example 2 says the following diagram is a net for a cube. So two-dimensional shape here. I can fold this up to form a 3D figure. That's what a net is. So they want to know, if you fold this thing up, this net, name the letters that will appear on faces that are across from each other, that are opposite. So here's my suggestion. You need to think of a piece of this net to be the bottom of your cube. So I usually go for a piece in the middle. Maybe I'll just do C. So I think of C as that's gonna stay put. That's gonna be the bottom, and I'm gonna fold this net up around it. So here's what I mean, and ta-da, got a giant net here. Let's say we pick C is gonna be the bottom. So I wanna fold my net up around that. So you'd take this and you'd flip it up. You'd flip B up here, you'd bring A around, E would come on top, and F would fold under. Okay, so I know having the net in your hand would make this a lot easier, but that's just kind of how you're quizzed and assessed in this class. I gotta be able to give you a paper copy of a quiz, and you've gotta be able to figure these problems out without actually being able to fold it. So if we did fold this up, like I said, B would come up, D would come up. So those two faces would be across from each other, D and B. When you bring A around this side, and you'd bring F around the exact same way, those two would be across from each other. C is gonna stay at the bottom, and since D would come up and A would fold over that to make the top of the box, E and C would be across from each other. If you would like to have one of these to practice with in class tomorrow, I'd be happy to do that. Okay, on the back. Oh yay, sketching, we all love this. So example 3 says, here's a net for another figure, another polyhedron, and they want us to sketch what the shape might look like. So same idea, maybe you want to fold it up around this middle piece, the bottom. So you'd fold this up, and the triangles would fold up as the ends. Here's how I draw this. So the two triangles, I draw those first, and your answers could definitely vary from mine, but here's how I would draw it. I would take the two triangles and kind of draw them staggered like that, and then I would connect all the points or all the vertices. And when they do dashed lines like that, remember that means you can't see that piece, it's in the background. And I guess I should have done that dash, but you get the idea. So it's got all the faces there. There's 1, 2, 3, 4, 5 faces. Mine's got the two triangles on the end, and then the other 3 rectangles. So there's an example of what that figure would look like. Example 4 is going the opposite way. So this time they give you the 3D figure, and they want you to flatten it out and draw the 2D net. So again, yay. I've got the figure right here. So it's a little pyramid here. They want to know, what would it look like flattened out? Well, if you kind of take this thing and unfold it, I'll show you this way, here's what it looks like. It's got that piece it's sitting on, which is a square, so I'd probably draw that in the middle. Okay, so the bottom of it is a square, and then it's got 4 triangular faces that are coming off of that. So again, it would kind of look like this if you unfolded it. So we're going to do something like this. Doesn't have to be perfect, we get the idea. All the faces should be there, and they are. All right, so that's going to be a lot of this lesson, you guys, being able to draw nets, draw a figure, kind of relate those two things. There's also something called Euler's formula. And what Euler's formula does is it relates the number of faces, edges, and vertices in a figure. So those three kind of key things we were talking about on the front. So here's what the formula is. It's the number of faces plus the number of vertices equals the number of edges plus 2. Don't you wish you were the person who discovered this? Good old Euler. Okay, so in any polyhedron, any 3D figure, if you add the faces and the vertices, that should equal the number of edges plus 2. So if they give you a crazy example like number 1 where it says some polyhedron has 24 different sides, 24 faces. I don't want to draw that. It's got 30 edges. No way do I want to draw that to figure out how many little points it's got. So I'm just going to use Euler's formula. I know that there's 24 faces, so I plug that in for F there. I know there's 30 edges, so let's get 30 plus 2 on the other side. I don't know the vertices, so we'll keep that in there. Okay, we all should be able to do that simple algebra problem. If I just add 32, and then I subtract over the 24, then I'm going to get that there's 8 vertices. So way easier than trying to imagine what this shape looks like or draw it out or count them yourself. So much easier to use Euler's formula. All right, the last example uses Euler's formula as well. It's just kind of a little bit more challenging than example 1. So this one says that in a certain polyhedron, it has twice as many edges as vertices. So that's definitely important. There's exactly 11 faces. I want to know how many edges and how many vertices does it have. Here's what I do. So I know I'm working with Euler's formula. I need to kind of figure out how these two things are related. So I'm going to make something up. And don't think this is the answer. I'm totally making this up. Let's say that there are 5 edges. Or no, let's say that there are 10 edges. So there's 10 edges, and I know that there's twice as many edges as there are vertices. So if there's 10 edges, then I know that there's 5 vertices. Because there's twice as many number of edges as there are vertices. So for these two things to be equal, and that's kind of what I have to set up here. For these two to be equal, I need to double the number of vertices. So I need to multiply this by 2. For that to actually equal the number of edges. So here's what I kind of just came up with when I did that. And maybe you could write this without even like making up your own example. But the number of edges, if I double the number of vertices, that gives me the number of edges. So I'm going to use that in Euler's formula here. So here's my formula. We'll plug in where we need to. I know there's 11 faces. You can't use V and E because if you use two variables, you're never going to be able to solve it. So let's keep V in there, but use substitution from algebra, you guys. Instead of using E, that's the same thing as 2 times the number of vertices. So let's use 2V instead. Then I would just subtract and get the V's together, and I would have 11 equals V plus 2. So it's kind of like a system. Yay. And then, okay, so there I get the number of vertices is 9. So if I come back to what I wrote originally, if I plug in 9 right there, I get that there's 18 edges. And you can use Euler's formula to make sure that it works. Well, let's see. Faces, that was 11. Plus vertices, so that's 20. And if I do the edges, 18 plus 2 Yep, that equals 20. So I know I got it right.